and also the final value theorems. So initial value theorem, we said h of 0 is equal to limit s goes to infinity s hs based on this table that we have. You can see here we have the initial value and the final value. This is for final value, this is for initial value theorems. So for the initial value, f of 0 is equal to limit s goes to infinity s fs, and fs here represent the Laplace transform of the function ft. We said in the time domain the function is ft, in the frequency domain it's become fs. So if I want to find the initial condition for the function in the time domain, it's equal to limit s go to infinity for s fs. That means I need to multiply fs by the frequency operator here, or Laplace operator. Also for the final value theorems, f of infinity, that means if I replace here, if I want to find how is the behavior of the function at infinity, I replace t by infinity here. So in this case, I want to use the Laplace transform to find this, because sometimes if I'm working in the time domain, I face some difficulties, or the function is more complicated, they have a lot of exponent and they have a lot of integral and so on, or derivative values. So it's easier to convert the function into the frequency domain by using Laplace transform. Then I apply the final value theorem for Laplace transform. So here in this example 4, we are going to see how to apply the initial and final value theorem on this function. I have hs is equal to 20 over s plus 3 times s squared plus 8s plus 25. This hs represents the Laplace transform for the function ht. So the function ht, I don't know what is the function ht here, but if I want to know the value of ht, I need to find the Laplace inverse for this function. Later we are going to learn how to find the ht from hs, or gt from gs, or yt from ys, and so on. Okay, so this we call it Laplace inverse. So now I already have the function here in the frequency domain, and I want to find the initial condition for the function ht at time equal to 0, and also the final value condition at for ht when t goes to infinity. What we need to do, we need just to write or to apply the property of the theorem of the initial value and the theorem of the final value. So for the case of the initial value here, I need to multiply hs by the value of s. So it's become limit s goes to infinity s, this is s here that I have from the formula, times hs, this is the value of hs that I want to use. Okay, after I apply s here, it's not correct that you go directly to substitute for infinity, because if you substitute for each s by infinity here, you are going to find the limit is infinity, and this is not correct. Okay, so what we need to do, same also we do previously when you learn in calculus how to find the limit for the function, limit for t goes to infinity, for example, for xt, or limit for t goes to or limit x goes to infinity for yx. Same, we are not going to directly substitute for the value. You need to do some amendment to the function here in order to make it easier to remove the infinity part. So what we did here, we divided over s cubic, for example, because if you have the highest power of the denominator here is s squared and s, so that means s squared times s will be s cubed. So s cube here, every every element here will be divided by s cube. So this one divided s square, s divided over s cubic, this one 3 over s cube, this one over s cube, this over s cube, this also s cube. Then here also the numerator will be divided by s cube. So what will be the result here? After you divide all by s cube and you remove the extra s from the numerator and the denominator, this will give you 1 plus 3 over s, 1 plus 8 over s, 25 over s squared. You can see here When you divide this one s square, you divide it by 1s square, and you divide this one by s square by s square, okay? The 3 by s square, and here you divide by s, here by s. Now you have s times s square. For this one s, for this one is s square. So s times s square is s cubic. So you have s cubic here in the denominator, and you have also as s cubic in the numerator. So what's the rest here? After you remove this one with the cube, it's become s square. After you remove this s with that s, it's become 1. After you remove 3 over s, so it's become 3 over s. After you divide s square over s square, it's become 1. 8s over s square, it's become 8 over s. 25 over s squared become 25 over s squared. Now you substitute for all values by infinity. So when you put infinity here, this is infinity, this infinity, here infinity as well, here infinity. Each s will be replaced by infinity. So 20 over infinity gives you 0, this one gives you 1, this one gives you 0, 0, 0, and the total will be 0. So this is how to apply the initial value theorem, or to find the initial condition for the function in the time domain, which is h of 0. The same will be repeated or will be done with the final value theorem. So the final value theorem here said h infinity is equal to limit s goes to 0 s h s. That means each s in the function will be replaced by 0. So you need to multiply the same hs here times s. Then you need to find the limit for this function when s goes to 0. Instead of infinity in the first case, here it's become goes to 0. Even we are talking about the final value here, but in the s domain it's become goes to 0. Even we talk about initial value here, but in the s domain it's go to infinity. So this is the property of the Laplace. Now we just have limit s goes to 0, 20s, the same function here, multiply by s, so it's become 20s, s plus 3, s squared, 8s, 25. In the case of s goes to 0, you can directly substitute for the value. No need to do any amendment or modification here in order to avoid the calculation for the infinite values. So here you just substitute by 0, this one 0, that one 0, that one 0. So you have 0 over 3 times 25. It will give you also 0 value. Is it clear how to apply these two properties? One clear to proceed to next slide. One not clear to stay in the same slide. All silent, that means clear. Next. So for the example 5 here, we are going to repeat the same application for the initial value and the final value, but for another function, which is gs here, is equal to s cubic to s plus 6 over s plus 1 square s plus 3. The same when you want to apply the initial condition value, that means you are going to multiply the function here by s, and then you are going to do a little bit modification to the function here in order to avoid the calculation for the infinite values. So here, this is the result from multiplication of s and divided by s here in the original. This is the s, the original s. Here the s from the formula. So this s will go with that s. Still have s cubic plus 2s plus 6 over s plus 1 all square s plus 3. Okay. So what's the, when you want to open s plus 1 all square, it becomes s square plus 1s plus 1, correct? So all square. This is after you open the square, so you remove the square. So s square plus s plus 1, okay? So now you need to open, this will be 2s, because you have s plus 1 times s plus 1. S square, s1 it is s, 1s plus s, 1 1 plus 1, so it's become s squared plus 2s plus 1. So now this is the function which we have here. We divide it by s squared for the first bracket, and we divide it for the s for the second bracket. So we have s squared, we have s here. So the total will be s cubic that we are going to divide the numerator for s cubic here in this case. So now I have s squared 1 plus, and this is s squared. We have here s cubic, s squared, because the highest is s cubic. I divide it by s cube. I divide it by s cube. I divide it by s cube. So I have 6 over s cube. I have 2 over s squared, and I have s cube over s cube. So it gives you 1. Okay. So from where I got this s cube, this one from the result of the, when I divide the numerator over a number, I have to divide also the denominator over the same number. Now I substitute for each s. After I do this, I remove this s cube with the s square. So it gives you 1 plus 2 over s square plus 6 over s cube over 1 plus 2 over s plus 1 over s squared times 1 plus 3s. In this case, you can go to apply the initial, to find the limit for infinity, because all s here are become in the denominator instead of in the numerator. So you cannot, it's easy for you to do calculation for the infinite values. So now 1 plus 2 over infinity, which is 0, plus 6 over infinity also will be 0, 0. Okay, so in the numerator here you still have 1. In the denominator you have 0 for this one, you have 0 for that one, and 0 here. So you still have 1 plus 1, which is 1 plus 1 plus 0, which is 1, times 1 plus 0, which is 1. So it is 1. So in the numerator here you have 1, in the numerator 1, in the denominator 1. So the initial value will be 1. Okay, clear? Any question until here?
No, sir, clear.
Okay, clear. So after Fourier series, everything is very easy. I know. Okay. Wait. Okay. The same is for the final value here. So in the case of final value, also you are going to apply the formula, but you are going directly to substitute for the value which is 0. So s here you have 0. Sorry. You have here s equal to 0. This one is 0. You still have 6 in the numerator. Here 0, 0. You still have 3 in the denominator. So 6 over 3 will give you 2. This one exercise, you can do it, and you already have the answer here. You can check your answer if it's correct or not. So this is all about the Laplace transform calculation and how we can find the Laplace transform either using the original definition, which is Fs is equal to integration from 0 to infinity Ft exponential negative St dt. This is the main definition for Laplace transform. And if I ask you find by using the definition or the main definition, you have to apply this formula to find the value of Laplace transform by using integration. And the second is to use the table that I provided for the commonly used Laplace transform formula for some function. And from that one, we can adopt to find the other complicated function. Okay, so this is regarding the Laplace. So how about the inverse Laplace transform? Inverse means I need to return the function from the s domain into the frequency, into the time domain. So I already have f of s. I want to return it again into ft. Why? Because we said if I want to use Laplace transform to calculate some or to solve some differential equation, the first step I need to convert this differential equation into algebraic sum by using Laplace. Then I solve the equation in Laplace form. In order to find the response or find the solution for the differential equation, I need to apply Laplace transform inverse. Okay, because usually the solution for differential equation, if you have t square over dt square xt, for example, plus 3d over dt xt plus 3xt. Okay, so the solution for such differential equation will be a function which is xt is equal to what? It's not the solution like the normal equation. Normal equation, when you solve, you need to find what is the value of the variable, what is the value of x, what is the value of y, and so on. But in the case of differential equation, the solution of differential equation will be a function in the time domain, for example, or in the x domain, and so on. So this function actually is come from these derivatives, because I do not have the function in this equation. I only have the second derivative, for example, the first derivative, and so on. So how to solve? To find the original xt. Usually, if you have easy or simple differential equation like d over dt, dx over dt, and you want to solve, the easiest way to solve is to make integration for this one. So the integration for the dx over dt, for example, will be xt. This is the for the simple one. But if you have a complicated differential equation, second order, third order, and so on, so in this case we are going to use Laplace. So we need to apply Laplace first to find the equation by using the derivative theorems here. Then we find the inverse Laplace in order to find the original function, which is x of t or y of t or f of t, and so on. So here we said it's not easy to use this formula that I shared with you last time to find the inverse Laplace transform, which is the formula that's based on the integration. So this is the original formula to find the inverse Laplace for ft. So the inverse Laplace here for fs will equal to 1 over 2 pi j integration from sigma minus j or infinity. You can see here it's a little bit complicated when you have some infinite value and so on. So what we need to do here in order to find the inverse Laplace, we are going to use the table that we have for the formulas, this table for the common formulas, that table here, and we are going to compare the function that we will be given. So if you are given the function which said fs equal to 1, so what will be ft? It will be delta t or impulse function. If you have fs equal to 1 over s, then the ft will equal to ut. That means from this table you can know what will be the inverse Laplace transform directly from the table. You have 1 over s squared, so the inverse will be t. If you have n, 1 over s plus f, for example, is exponent negative 80 and so on. So this table is very important to find the inverse Laplace transform and Laplace transform as well. But for inverse is more critical, because for Laplace it's easy to apply integration for each function and you can find its inverse, its transform function. But for the inverse, somehow it's complicated and you need to perform some simplification in order to find the inverse Laplace transform. So what we can do if our transfer function is none of these functions? I do not have 1 over s alone. I do not have 1 over s plus 2 alone, 1 over s plus 2 square alone, and so on. So I have a complicated function which consists from multiple of these functions. So my task will be how to simplify my transfer function here, or my function in the S domain, to be more close to any of these functions. So in that case, it's easy for me to find the inverse Laplace for it. Okay, we are going to see examples, but now I want you to know if your function in the S domain is one of these functions, directly you can use the existing function here as inverse. 1 over s plus 2, it will equal to exponent negative 2t. 1 over s plus 5, for example, here, whatever is the value, so you just find it in the S domain and you substitute for the missing variables. You have b over s squared plus b squared, you need to convert it into sine bt. If b is equal to 2, so this becomes 2. If b equal to 5, this becomes 5, and so on. But if you have Laplace transform function, which is more complicated and you cannot find it in any of these functions, so in that case you need to apply some simplification to make it close to any of them, then to find their inverse Laplace transform. So that's what we are going to do in this calculation here, how to find the inverse Laplace transform for any function. And before we go to the process how convert or how to find inverse Laplace transform for some function which is complicated and not available in the table, we need to know that the transfer function here usually consists from the Laplace transform function in the S domain usually come from in this form, for example, ns numerator over denominator. So you have in the numerator you have some values, and you have in the denominator some values of s. When we say n of s, you expect that you are going to see s squared plus 2s plus 3, for example, s cubic plus 5, s squared plus 2s plus 1. So if it's n of ns here, it will be one of these, it's a function of s in the numerator and also a function of s in the denominator. Okay, so these values in the numerator, if we make it equal to 0, it will give us some values. I mean, if I analyze, if I have s plus 2 and times s plus 3 in the numerator, and they have s times s plus 5 in the denominator times s plus 6, for example. The question here, what are the values that will make my the numerator of this function is equal to 0? When this numerator will equal to 0, at two values only, which is if the s equal to -2 and if s equal to -3. So these two values will make the numerator and also the total function here is equal to 0, because if s equal to -2, so this become -2 plus 2, so give you 0. 0 times any number will be 0 over any number, it will be 0. For that, we call these values which make the numerator equal to 0, we call them the zeros of the function. So whatever is the function here, is the transfer function or normal function, is it a voltage function, is it a current function, or is it a power function? So at the end, these values will make this function is equal to 0. So we call them the zeros. In the case of the denominator here, if you have any of the s operator can make the denominator is equal to 0, that means if your denominator is equal to 0, means transfer function is equal to infinity, because any number over 0 will give you infinity. Okay, so what are for this transfer function, for example, we have three values which make the transfer function denominator is equal to 0, which is s equal to 0, s equal to -5, s equal to -6. So these three values, we call them the pools of the functions. The pools means the value which make the denominator of the function is equal to 0. Thus, the overall function will become infinity. Okay, I want you to take note about these zeros and pool, because later on we are going to use them directly in our calculation to find to test if this transfer function or this function can be go for the first using the partial fraction method to convert it into the inverse Laplace transform. Okay, so the inverse Laplace here, in order the steps to find the inverse Laplace transform for the function which are not available in the table here, we need to compose the fs into a simple term using partial fraction expansion. So partial fraction, that means you have a complicated function, you are going to convert it into some values which is multiplied by each other, and there is summation or subtraction between them. So instead of have s squared plus 2s plus 5 over s cubed plus 2 plus 2s squared plus 3s plus 2, so you are going to use it in the form of partial fraction, so it's become easier for you to find it in your table of the Laplace transform that we see before. Okay, then after we convert it into the or by using the partial fraction method, we are going to find it directly from the table. So to find its inverse for each part of this function. So this function, for example, become in this form: 1 over s plus 1 plus 2 over s plus 3, for example, like this one. Okay, so this is how the partial fraction will be convert this complicated function into a simple function consists from multiple parts. So we call it partial fraction method. Why I need to do this? Because I want to check then in the table what is the inverse of 1 over s plus 1, what is the inverse of 2 over s plus 3. So it's easy for me to calculate or to extract from the table of Laplace transform and Laplace inverse transform. So this is an example how to calculate the inverse Laplace transform without using the integration method. I mean, you have the function here, fs is equal to 1 over s plus 3 all square. Okay, so this function actually is you can find it directly from the table that we have. So we already see such formula, which is 1 over s plus a square, for example. So if you go back to this table, you can find the transfer function for such function which equal to exponential negative. Here you have a is equal to 3. If we go back just to the table here we have 1 over s plus a all square, correct? So s here or a in that function is equal to 3. So you just need to substitute for 3 here. If this is 3, this become t exponential negative 3t directly. Since the function is existing or similar to one of the functions in the table, so you just directly you will say the inverse Laplace for this one is t exponential negative 3t. That's what we did here in this example. Since the function is available in the table, just use it as it is, and you can see here fs equal to 1 over s plus 3, this a equal to 3, you just substitute, so become exponential negative 3t ut. So this is the inverse Laplace for this function. And this we can do it directly because similar function is available in the table, which is 1 over s plus a all square. So we just go directly to the table to find it this value. But if this value is not available, I mean it's not in the table, so in this case you need to apply the partial fraction. This is another example here. You have fs equal to 3 over s minus 5 over s plus 1 plus 6 over s squared plus 4. So you have a function here consists from 1, 2, 3 parts, and this according to the linearity form or the linearity property of the Laplace. So you just apply Laplace for each part here. So that means we have Laplace for Laplace inverse for the first part, Laplace inverse for the second part, Laplace inverse for the third part. So as we can see here, if I want to find the inverse Laplace, that means I want to return this function into the time domain, okay, into its original form. So I need to apply Laplace inverse for this function. So I have Laplace inverse for the first part, Laplace inverse for the second part, Laplace inverse for the third part. So now for the first part, we did 3 over s is available in the table. So that means you have 1 over s, you have 2 over s, 3 over s, all are the same. So when you want to apply the the inverse Laplace for any number over s, this will give you the value of ut, because we said ut, when you find the Laplace for ut, will give you 1 over s. So if you have 2 ut, so it's become 2 over s. If you have 5 ut, so it's become 5 over s. So in this case, we have 3 over s. That means the inverse Laplace will be 3 and times ut here. So this is 3 ut. So 3 ut. And usually when we find the inverse, we need to multiply by ut because we know all the value of Laplace are greater than 0. Okay, there is no value for Laplace before 0. Okay, so we are talking about ut here. That means the function is greater than or equal to 0. Okay, so this is for the first part. The Laplace inverse for 5 over s plus 1. So also this available in the table because I have 1 over s plus a, for example. In the table, I can find 1 over s plus a. So what is the value of the s here? I mean, the value of the a is 1, for example. In this case, it is 1. So what I am going to do, just write 5 exponential or exponent here, negative t, because I have a is equal to t. The inverse of 1 over s plus a is exponent negative a t according to the table. Okay, so you just substitute for a here, which equal to 1. So it gives you exponent negative t, and the 5 here is the magnitude, so it's just 45, and the function will be multiplied by ut because it's greater than 0. Okay, the third part, which is Laplace inverse for 6 over s squared plus 4. So if we go back to the table here, we have 6 over s squared plus 2, which is one of the sign. As you can see here, we have sine bt is equal to b over s squared plus b squared. So the s plus 2 here in the numerator here represent the value of b. Here we have b, here we have b, b squared. If we go there, we just use this formula in order to find the inverse, which will be sine bt. Okay, so this will be, what is the value of b here? The value of b is 2. So this is 2 square actually. This is 2 square. 4 is equivalent to 2 square, which is equal to b square. And here 6 value, the value of 6 here is equal to, if b is equal to 2, that means this will be 3 times 2, 3b, correct? So the 3 here become there, still the magnitude, and the 2 over s squared plus 4, the inverse Laplace is sine 2t. Okay, so this is how to use it or how to calculate the inverse Laplace for some function which is either available in the table or can be converted easily into a value of function which is available in the table. But in the case of the function are not available, so in this case you need to apply simplification. You need to apply the partial fraction method in order to simplify your transfer function. Is it clear here? Any question about this example? No. The weather is not for question, correct? Next. Okay, inverse Laplace transform here. This is the show the procedure how to apply inverse Laplace for the differential equation. Just a step. We apply Laplace for both sides. Then we find the function which is y(s). Then we use algebraic sum to do some calculation. Then perform partial fraction expansion. So this is our concern here, or our focus in this part would be how to use the partial fraction method in order to simplify the transfer function. Thus we can easily find the inverse Laplace transform. So as we said here, the function consists from two parts, which is the numerator and denominator, and the numerator is responsible to generate the zeros of the function, and the denominator here to generate the poles of the function. Okay, so if the function, I mean, if the number the degree okay, if the function here, I mean, if the numerator is higher than the denominator, that means the degree or the order of the numerator is higher than the denominator. Like what? Like if we have the function is s cubed plus 5s squared plus 2s plus 1 over s squared plus 2s plus 3. So now the order of the equation or of the function in the numerator is higher than the denominator. So in this case, we cannot or we do not need to do the partial fraction. You just need to apply the long division. So you can divide the numerator over the denominator in order to simplify this function. Okay. But in the case of you have the order of the numerator and the denominator either the same or it's the numerator is lower than the denominator. So in this case, you need to apply the partial fraction. So how to apply partial fraction here? You need to simplify. I mean, you are going to find the roots or the roots for the denominator here. So you are going to assume, for example, this is we use the form here P1, B2. That means this is related. To highlight that this is the pools. We said the numerator is zeros. The denominator is the pools. So you have S plus P1, S plus P2, S plus P3. So this is how we can convert the denominator of our function. Then if these pools are different, that means I do not have similar pools. I have like the function is like this one, S plus 1 times S plus 2 times S plus 3. So none of these pools are the same. 1, 2, 3, 5, 10, 7, and so on. So the pools are not the same. So in this case, we call the pools are real and distinct. Real and distinct means they are real value. We do not have a complex number. We do not have imaginary values. So all the roots for this function or characteristic equation in the denominator here, all the roots are real and are differs from each other. So they are not the same. S plus 7, S plus 8, S plus 3. So they are not the same and they are real values. So in this case, we call it the case 1, and in this case, we are going to simplify the function into this form. So we have a1 over S plus 1 plus a2 over S plus 2 until an S plus pn. Then we are going to find what is the value of P1, what is the value of, A1, A2, A3, and so on. So we are going to convert the complicated transfer function into a simple partial fraction function. So later, this every part from here, I can find it easily in the table and find its inverse Laplace transform. We're going to have example about this one. But before we go to example here, you can see here how if we have this function here, this is as if this function is fs. So fs is equal to 1 over s plus a times s plus b times s plus c. So you have three roots, which is negative a, negative b, negative c here, and they are distinct. They are real number and they are distinct. For example, in this case, should be real number and should be distinct. What I need to do here, I need to apply partial fraction. So the partial fraction here become like, I assume this equal to a over s plus a plus b over s plus b plus c over s plus c. Whatever is the value of a, b, c, we are going to see how to calculate this value. But the main thing here, I want to show that this function is not easy to find its inverse directly from the table. What we do here, we convert it into three simple parts, and each part here can be easily found in the table of the Laplace transform. So I can easily convert it to inverse by using inverse Laplace. So if I want a over s plus a, so this become a is the magnitude of the value, whatever is the value here, 10, 100, 1000, doesn't matter. But the main thing is I have s plus a here. I can convert it into its inverse by using the formula exponential negative at according to the table. I have here b, s plus b, the same here. The b is there, is the magnitude, exponential negative bt ut. C, the same is value. So this is how, for the first case, it's simple to find this inverse Laplace transform for any function. So for 1 over s, give you ut, 1 over s squared give you tut, 1 over n over s plus n. This gives all this value. You can find it in the table. So our case here is exponent. So exponent negative a tut. You are going to apply for these three parts of the function. So now we are going to see how we can calculate the value of the numerator for the partial fraction method here. So if you have this function, which is fs or gs or any function here, and you want to find its inverse Laplace. So you have k over s plus a, s plus b, s plus c, and he said x over s is equal to 1 over s. This is given the value, the input for your system, for example. So if you want to apply or to find the ys here, you need to ys is equal to xs times this function. So xs already given here, 1 over s. So it become like this one, k over s, s plus a, s plus b, s plus c. You have 4 pools now. One at 0, one at negative a, one at negative b, one at negative c. I want to apply partial fraction, so it's become 4 parts. So a over s, b over sa, c over s plus b, and d over sc. Not realize that all uh, pools here are different. They are not the same. So the first, for example, is 0. The second is negative a. The third is negative b. The fourth is negative c. So all real and all are distinct. Are not the same. Okay. Now I split them. I split this function into these 4 parts or 4 simple parts. Now what I need to do, I don't know what is the value of a, what is the value of b, what is the value of c, what is the value of d. So my task here will be to calculate these magnitude values or gain values by using this formula. So when I want to find any of these gains, I just need to multiply, or the value of a here is equal to s times y, equal to the function here ys, the original function, which is this one, okay, times its denominator here. The denominator of the first part is s, so I need to multiply by s when I calculate a. The denominator for b is s plus a, so I need to multiply times s plus a. The denominator here s plus b, I need to multiply s plus b, and here s plus c, I need to multiply by s plus c, and I substitute for the value of s is equal to 0 in the first case, is equal to negative a in the second case, is equal to negative b in the third case, and negative c in the fourth case. This is the partial fraction method. Is one of the methods that you supposed to be already learned either in calculus or in other courses. Okay, but here we are going to take some example just how to use this partial fraction method.